Okay, so after some flight delays, we're very happy to have Sally Benson here with us to give a plenary here with the title that you will show in a minute. And Sally Benson has been working in the area of CCS for many years, and she's a groundwater hydrologist and a reservoir engineer, and I think you have conducted research far beyond these issues and a quite wide range of different aspects on carbon capture and storage and also BECCS. So please, Sally.
Okay, well, thank you very much. It was really great to walk into the room and see so many people here who were interested in negative emissions. This is actually a topic that I started working on, I think it was about 2011, and I am the director of something called the Global Climate and Energy Project, and we decided to hold a workshop on this topic. So anyway, it's really terrific to see all of the enthusiasm for this. I apologize for being late. We were sitting in Frankfurt and everything was supposed to be fine, and all of a sudden they had to switch our plane. So that's why I'm late. So I'm going to be talking about geological storage of CO2 for negative emissions. So I'm glad you gave all those tough questions to Mike Monia about, isn't it just perpetuating the use of fossil fuels? So you'll see I qualified this talk to be specifically about negative emissions. The two major pathways where this is interesting are one combined with bioenergy, so BECCS, bioenergy plus CCS, and also in ethanol refining where there's a pure source of CO2 that's emanated in the fermentation. That's another good example. And also one day, if we are able to economically capture CO2 from air and we need to dispose of that or sequester it, we could put it underground as well. So those are the two pathways, and there are probably more, but since I'm kind of jet-lagged right now, that's the list I'm going to give you. Okay, so I'll talk about three things. First, sort of CO2 storage basics. I kind of assumed that we had a very heterogeneous audience, and so for those of you who know all of the things I'm going to say, I apologize. Hopefully I'll say it in a new way that's interesting. And for those of you who are not so familiar with the deep subsurface, I hope that it gives you a sort of fundamental understanding that then we can engage in a dialogue about. I'll then talk a little bit about the status of CO2 storage today, how much we're doing, where are we doing it, and then I'll wrap up with some specific considerations for CO2 storage around negative emissions. Okay, so just the most basic of the basic. The idea is that if we have some kind of source of CO2 from a power plant or a BECCS plant or from direct air capture, typically we would capture that as a gas. We can then compress that into a liquid where we can put it into a pipeline, where we could transport it to some place where we could pump it deep underground with the idea that it is essentially permanently stored. So that's basically the idea, not that it's and there's a long history to why we use the word storage. In the United States and in Australia, sequestration was used more prevalently, but the Europeans didn't like the word sequestration, and so we sort of all adopted storage as a way of describing this. So that's the basic idea. So then the question is where can we put the carbon dioxide underground? So the sort of most obvious is that we could go to places where we've pumped out oil or gas, and in the process of pumping out that oil or gas, we've taken fluids out of the pore space, which reduces the pressure. In essence, we've sort of made some room where we could put fluids back in. So depleted oil and gas reservoirs are an opportunity. There's also, as Michael Monia said, the opportunity to couple that with enhanced oil recovery. I think if we're interested in negative emissions, we probably don't want to couple that with enhanced oil recovery, but it's certainly possible you could pump way more CO2 into an oil field than you take oil out, in which case you could actually achieve negative emissions even in that way if you wanted to. Next main option is to put CO2 in what are called saline reservoirs or saline aquifers. These are rocks where the pore space is filled with extremely salty fluid, so salty that we certainly wouldn't want to drink it, and that we also don't have other applications such as irrigation or livestock feeding or whatever. Okay, so that's the next option. It turns out you can also put CO2 into coal. It actually reacts with the rock and it absorbs to the rock and in essence remains stuck there. And then there are other options that are coming along now that are actually quite interesting. One possibility is to put CO2 into basaltic rocks. Where the CO2 can react with the minerals and form carbonate minerals like magnesite and so forth. So, and these are just being developed. There's a very nice project in Iceland that has been going along really well where they've been able to demonstrate this technology. There's also quite a bit of discussion about trying to put CO2 into shale. As you might know, in North America, there are many wells that have now been drilled into shale, and they tend to deplete quite quickly in terms of gas production or oil production. And given that these wells are there, perhaps that could be a storage option as well. But really the most mature options are to put CO2 into what we call sedimentary basins, where the pore spaces are either filled with salty water or filled with oil or gas, or the void space that's been left after that. So those are our options. So what do these deep geological formations look like? So here's a picture of one. This is actually in Northern California, right near where I live. And this is the great Central Valley of California. And you can see it's quite large, about 200 kilometers from coast to the Sierra Nevada mountain range. And at its greatest depths, it's about 6 kilometers deep. So an enormous volume of sediments. And you'll notice there are two colors. There's the yellow, and this is sandstone. So imagine basically beach sand that's kind of been consolidated into a rock. It's got pores, you can see the individual grains and so forth. And then the second are the shale, and these are the gray areas. And picture what this is just basically mud or clay that has been compacted over time, and it has very tiny pores, sort of nanometer scale pores in those rocks. And this layer cake geology is typical of sedimentary basins, and in fact it's exactly what we need for CO2 storage, because we want to pump the CO2 into the sandstone formations, and we want there to be a shale or some other kind of sealing rock on top of it so that it will keep it in the subsurface. So that's basically the idea. So that's one example of what one looks like. And actually in this is the northern part of the valley, and there's actually a lot of gas reservoirs that are, lots of gas are trapped in those sands beneath those shales. So we know not only in principle, but we know from geologic analogs that you can trap buoyant gases in these kind of layer cake geologies. So that's that. So the question is you might say, well, are there lots of these? And so this is a map. It's color-coded in 3 areas. So the darkest areas are what we consider highly prospective. That means that if we were to go look for a place to do CO2 storage there's a good possibility that we would find a suitable site that's deep enough, that has a nice sand reservoir with a nice seal over it, and so forth. Then there are the light, sort of medium gray, and those are called prospective, meaning that we think that it's got the right type of rocks, but we probably haven't explored it very much. Much of the exploration, or much of what we know about the geologic formations, actually comes from the oil and gas industry who've drilled these areas. So if there's an area that hasn't yet been drilled for that purpose, we often lack information. So anyway, those would be reasonably good places to look. And the lightest color are areas where we don't have sedimentary basins. There are either igneous rocks or metamorphic rocks that are not suitable for traditional geologic storage. Having said that, though, if we look at India, which doesn't have a sedimentary basin, there's actually extensive deposits of basalt. So if we were able to perfect the technology of converting CO2 into minerals by putting it into basalt, even places like India would have quite an interesting capacity. So sort of the bottom line is it's widespread, the capacity, but it certainly isn't everywhere. So you can't just think you're going to, everyone's backyard. You've got to go find the right places. Okay, so that's about the rocks. Now what I'd like to talk about is the CO2. So the CO2 is captured as a gas, and then when we compress it, it can be converted into a liquid. Okay, and the liquid actually has properties, a density fairly similar to water as long as the CO2 is cold enough. However, as we go deep into the subsurface, we have our geothermal gradient. It gets warmer and warmer, and the CO2 goes into the space that's called supercritical fluid. So for deep enough, we would expect to be storing CO2 in a supercritical fluid. And again, this is beneficial because it's dense. It's not as dense as water. It's typically about 2/3 the density of water. And on the right-hand side, there you can see that red line. That's basically the density as a function of depth. So you can see to about 800 meters, it's still a gas and it has very low density. But once it gets beneath that about 800 meters, it's a supercritical fluid and has this high density that is about 2/3 that of water. Okay, so why is it important that it is dense, that is, it's in a dense phase? The first one is that although there's lots of pore space to put CO2 in, it's not unlimited, and we want to be able to access it efficiently. So the denser the fluid, the more efficiently we can store CO2. And then the second reason that's also very important is that since CO2 is lighter than water, it's buoyant and it wants to float up. It wants to try to escape, right? So the denser it is relative to water, the less these buoyancy forces will be. So these are the two reasons that we would like this dense fluid, and typically below about 800 meters or so, you achieve those conditions. Okay, so CO2 is lighter than water, and so that brings us to sort of the basic scheme for CO2 storage, and this is just a little cartoon. So what we saw in this is that we injected CO2 near the bottom of this storage reservoir, this sandstone as an example, and because it was lighter than water, it wants to float up. However, when it reaches this seal, this very fine textured nanometer pore diameter rock, the interfacial tension between the fluids actually creates a sort of a membrane, and the CO2 can't migrate through that seal. So this is the basic idea. Now, of course, it's much more complicated because rocks are much more complicated than this little homogeneous model. But that's the basic idea, is that you want to put it into a reservoir where it then is going to float up and rest against the base of this seal. Okay, so just to be very clear, so about what keeps CO2 underground. The primary trapping mechanism is the presence of this seal rock, a shale or a salt, an anhydrite or something like that. Okay, and it provides a barrier that acts with two types of physics. One, it's a permeability barrier, meaning that if you have a pressure gradient, it takes an enormous pressure gradient to try to drive the CO2 through that rock. So that's one set of physics. The other set of physics is that it actually is a capillary barrier, and the interfacial tension between water and CO2 is great enough that the CO2 can't enter the very, very tiny nanometer scale pores. Okay, so that's the main thing. But it turns out that there are actually other secondary trapping mechanisms that over longer time periods, they will continue to increase the security of storage. So the first one is CO2 dissolves in water. We all know that. We drink fizzy water all the time. Once the CO2 dissolves in water, actually the water becomes slightly more dense, and then you start developing convection cells, and if you had long enough and if you had a large enough area, eventually even conceivably all the CO2 could dissolve. The second thing that happens is that after you stop injecting, the water wants to come back where the CO2 was, and as it invades into the CO2 plume, it creates disconnected gas ganglia. And once the gas bubbles are disconnected, it is no longer mobile. You can't move it. So that's this little picture on the right. This is a little micro X-ray CT image obtained at a synchrotron, and those little brown bubbles are actually little CO2 bubbles, and the gray is water, and that's an illustration of trapped CO2. And then finally, if you have the right types of rocks where you have a sufficient amount of cations, CO2 can be converted to solid minerals. Okay, so that's the basic physics behind why geological storage should safely and permanently store CO2. So now what I'd like to do is I'm just going to give you a bunch of examples of real data from different sites using different mechanisms to sort of give you an appreciation for how much we understand about the fundamentals of this. And I'll just start with this little image here. This is at the Advanced Light Source. This is a synchrotron X-ray source. And we have a sandstone rock, and we put this into the beamline, and we can reconstruct three-dimensional images, and we can see the rocks, and we can see the CO2 bubbles, and we can see the water. And so that's what this picture up on the right is. The red are the rock grains, the green is the water, and all of those little black blobs are, again, these disconnected ganglia of CO2 that in this case are trapped in the rocks. And the individual pores in this rocks are on the scale of, say, 100 microns or so, which is fairly typical for a sandstone. So we can actually, visualize this with the most advanced tools that are available today. So we can also move up in scale. We do a lot of imaging with medical CT scanners, and that gives us, we don't see individual pores. Instead, we can look at for things like the influence of the structure of the rock on the behavior of the CO2 in the rock. And we can conduct experiments over weeks and months, really, as long as the graduate students are willing to keep these experiments going. And when we can look what happens to CO2, and here's just another example of that. So on the top, this is, again, a medical image of a rock. And what's graphed here, or what's shown there, is the porosity, and the fraction of the rock that is void space. And you can see it's got these different layers in it. And on the bottom, we just show an image where we start out with a water-filled rock, which is the way it is in the subsurface in the saline aquifer, and we pump 100% CO2 into that, and it displaces some, but not all of the water. And we can see that, and we can also now see in great detail how the influence of the rock structure impacts the CO2 behavior. And this is really important when we are looking at real formations, because all rock formations are so heterogeneous, and these kind of studies give us great insight. We can also see for this example that we are only 29% or 29.5% of the pore space is actually filled up with CO2, and that's pretty typical. And the reason that we can't completely displace the water is because CO2 has a very low viscosity. It's like 1/20th the viscosity of water, so it's difficult to push the water out of the way. So even when we have a storage reservoir, not 100% of the pore space is filled up with CO2. It's a mixture of CO2 and water. So now let's move up to a slightly bigger scale. This is actually in your neighborhood. This is really the most iconic and sort of famous project in CO2 storage. One, because it started very early, but probably more importantly is a lot of data has been collected, and this data has been made widely available to the research community. So we all like it because it's so helpful. So this was a project where natural gas is pumped from deep in the subsurface. That's that orange or dark red layer on the bottom. But the gas has too much CO2 to sell, so they have to separate the CO2. And Norway has a tax on offshore CO2 emissions. So instead of venting the CO2 and paying the tax, they said, well, let's see if we can safely pump it underground and see what happens. So that's what they did. So on the left is the CO2 capture unit that captures it and then pumps it underground. And the most important thing they did was something called seismic imaging. And for those of you who are unfamiliar, just think of it like a sonogram for the Earth. You can get an image of the sort of density contrast and compressibility contrast of the rocks. And when CO2 is present, it's much more compressible, so it actually kind of lights up the subsurface, and as you can see. And when this project was started, they really didn't know how well it was going to work, but it really demonstrated that seismic imaging is a fantastic monitoring tool, and this is really now the gold standard in the industry for keeping track of where your CO2 is. So just to show you what this is, on the left-hand side, the top panel is a cross-section through the Earth. The bottom panel is like a map view. And so that was 1994, before any CO2 was put in. Started in 1996, and this isn't all their data. This is just some of the snapshots that sort of nicely illustrate what's happening. And by 2001, you start seeing that the subsurface looks very different. Well, those correspond to layers of CO2 trapped beneath shale layers within the sand formation. And then you see at the very top that the CO2 is contained beneath a very large and thick regional seal. And on the bottom image, you can basically watch this, what we call a plume, growing over time. And there's a scale bar, about a kilometer. So by 2001, we have about a 2-kilometer long plume by about a kilometer wide. And it grows over time, which is what you would expect it to do. So again, we can actually see what happens. And this isn't the only technique for monitoring what's happening with CO2. This is another project. This is a very interesting project. This was the first time CO2 from an ethanol plant was sequestered. And they did a pilot program of 300,000 tons per year for 3 years. And they've just upped this to 1 million tons a year. At this particular site. And this is some work that we were doing, asking the question, if you had pressure sensors distributed throughout the storage reservoir. Okay, so if you look at the image on the left, the gray Eau Claire formation, that's the seal. And then the yellow is the big storage formation, and they were actually just injecting at the very, very bottom of it. And then there was a monitoring well about 300 meters away, and we had all these pressure sensors, because pressure is pretty easy to measure, and you can measure it continuously. So our question was, well, can we use this kind of data to tell where the CO2 plume is moving? And not to belabor this, but this is pressure data from a bunch of sensors. You'll see some of them look very similar, some of them look quite different. That's where the information is. That's what's telling us about the CO2 plume. So by doing data inversion or history matching, we're able to come up with our projection of, or our prediction of where the CO2 plume is going. And this is after 4 months and after 8 months. And we predict it's going out in these long little stringy things, basically on these high permeability pathways. So this is what the pressure data told us. And it turns out that they, every once in a while, would go in and directly measure what's called the saturation, or the fraction of the pore space filled with CO2. And that's the image on the left. This is the injection well itself. And so wherever you see the red, that's the indication of where the CO2 is. So at the injection well, you do expect the CO2 to be along that whole section. But if we look at the monitoring well, you can see at like 4 months, 6 months, 9 months, you start to see little thin streaks of red. And that's exactly what the pressure data was also telling us. So again, we have more methods to figure out where the CO2 is going, and we have a pretty good understanding of how the complexity of the rocks influences CO2 behavior. So this is another way to monitor CO2. So one of the questions is, well, what if it's leaking at the surface? What if you had a bunch of fissures or faults and fractures and the CO2 was somehow migrating from great depth and gotten it to the surface? Could you detect it? And this is actually an experiment we did out in Utah, where there are naturally occurring seeps, and it's known where these are. And so we got the idea of taking a very sophisticated cavity ring-down spectrometer that could measure C12 and C11, and basically in a mobile platform, basically see if you walked around with this highly sensitive detector, could you actually find where the leaks were? And that's this little trail. So we had this mule had a GPS, and he was carrying this instrument, and the inlet tube was right on his foot, and he was able to find all the known CO2 seeps. And we then went on and did a controlled experiment where we intentionally created a release. So what we actually did is we put a 100-meter long horizontal well about 1.5 meters beneath the surface. We knew exactly where it was, and we could carefully control the amount of CO2 that went into each of the zones. And then we knew where the water table was, so we knew it would leak up towards the surface. And there were a whole bunch of different teams. We had eddy covariance towers, we had hyperspectral imaging, soil gas, flux accumulation chambers, so many different techniques, and actually everything worked pretty well. And what we were particularly interested in, again, is our mobile sensing platform. So on the left is the footprint of the experimental site. Where the black is, that was the line where this well was. And again, this is a Picaro instrument. I'm kind of guessing there are quite a lot of you who are familiar with this instrument. And on the right-hand side is a map. So we just did many, many traverses, and we just asked the question, how many times when we went over this leak did we detect it? So do we have a high degree of certainty? And it goes from 100% to 0%. And you can see in the vicinity of the well, we almost always were able to detect it, regardless of the wind, regardless of the time of day. And this was a very, very, very small leak rate. So again, if CO2 is leaking at the surface, we have ways to look at that. So another really important tool for CO2 sequestration is simulation. And many research groups around the world and private companies have developed simulators that take the physics and chemistry and implement it with spatially and temporally resolved sets of coupled partial differential equations, and basically can use these models to simulate how a plume will evolve over time. And in particular, these are used for design to figure out where the CO2 will go. How do you control the pressure buildup, because you don't want the pressure buildup to be too high? And how do you optimize operation of the site? So that's what these models are. And on the left is just an example of a geological model that was actually used to predict what we see on the right. And this was how this plume of CO2 would evolve over 1 year, 2 years, 5 years, and so forth, up until the end of the injection period, which was at 20 years. And at 20 years, we stopped injecting in the simulator and let the plume basically equilibrate gravitationally with the surrounding water. So these kind of tools are available. So that kind of leads me to our current best understanding of, in a conceptual way, about what we could expect for the risks of a geologic storage project. And this is a cartoon, but it's designed to kind of get across a couple of points. So the first thing is, well, so basically on the x-axis we have time, and it's in multiples of the injection period. So say if you have a 30 years injection, that might be a typical project, so that we'd have time 0, 30 years, 60, and so forth. And then on the y-axis is environmental health safety risk. And this is not one single risk. This is a proxy for leaking CO2, a proxy for pressure buildup, a proxy for potential for leaking salty water into an overlying fresh aquifer, and so forth. Okay, so that's the way to read this. Okay, so the first thing is that there are regulations that basically set an upper limit on the amount of this sort of tolerable risk, and sometimes it's set in terms of percent leakage, like 1% leakage over 1,000 years or something like that. So regulators basically give some performance requirements. And then a developer doing a project is going to figure out, their injection scheme, their number of wells, to make sure that, that you would never, if the project goes well, exceed those. So that's sort of your design basis. So you look at your site characterization and selection. You would go and survey whether there are any active or abandoned wells in the region that could be a vulnerability, and you would design how quickly you inject, how many wells you need, and so forth. So that's your design basis. And so your goal would be that your project will never exceed the risks that you anticipated. So when you first start doing a project, you're for the first time putting CO2 into a reservoir, the pressure is building up, so that the risk of something going wrong is actually increasing over time. Now, during this whole time, you're monitoring using the kind of tools that I described, and you're also running your model and sort of recalibrating your model, because the subsurface is complex and sometimes we can't get a very detailed model until we start injecting or extracting fluids. So all that time we're making a better and better model. Okay, and at some point we actually have a pretty good model. We know that our wells aren't leaking and so forth, and the risk levels off. Okay, so then we stop our project. We stop injecting. The pressure starts to go down. And the risks, once the pressure starts to go down, the risks of leakage and groundwater contamination all go down. Okay, and then they're going to continue to decrease over time. So that somehow the idea that you do a project and that it has an increasing liability over time, like we're leaving something bad for our children to deal with, this is actually quite the reverse. The biggest risks of these projects are during the active time where we're injecting it and so forth, but we're also actively monitoring it. So this is just a paradigm, at least the way I think about this. So now to go to what others have said about security of CO2 storage projects. The IPCC did a special report in 2005 that involved over 32 experts on the geologic storage chapter alone. And basically this group concluded, and I'm just going to read it because these words were very carefully discussed ad infinitum. So basically, the fraction retained, meaning the permanence, at appropriately selected and managed geologic storage reservoirs is likely to exceed 99% over 1,000 years. So this was an expression that if you find the right site, the CO2 should be permanently stored. The second thing had to do with risk to ecosystems, risk to groundwater, risks to workers, risk to the public. And so here we said, with appropriate site selection informed by available subsurface information, a monitoring program to detect problems, a regulatory system, and appropriate use of remediation methods, like if you find you have a leaking well, you have to go fix it, as an example, that to stop or control CO₂ releases if they arise. The local health, safety, and environmental risks of geologic storage would be comparable to the risks of current activities such as natural gas storage, EOR, and deep underground disposal of acid gas. Now, you notice we don't say that there's no risk. We say that this is very equivalent to current activities, and I will leave it to you all to make your judgment about whether those are acceptable risks. But basically, these were intended to provide confidence that this should be an effective approach for reducing greenhouse gas emissions. So what was the basis for this? The mere existence of oil and gas reservoirs proves that you can store buoyant fluids in the subsurface for geological time periods of millions and tens and hundreds of millions of years. That's the first thing. The second thing is that these kind of activities are analogous to things we do a lot of today. There's over 40 years of experience with injecting CO₂ for enhanced oil recovery, 100 years with natural gas storage, and more recently, particularly in Canada, lots of experience with acid gas disposal. And by and large, these go very well. And then finally, now here we are in 2018, and there's over 20 years of experience with commercial CO₂ storage projects. Sleipner, of course, being the longest standing one, but today we're capturing and sequestering 31 million tons a year in over 21 different projects. And there have been innumerable, very small scale projects in addition. So here's a map showing the location of commercial and demonstration CO₂ projects. And as you can see, quite a lot in North America. Norway, of course, a leader in this, but Australia as well, being heavily engaged. So what have we learned? And I'm just about to wrap up. So in terms of the fundamental storage and leakage mechanisms, we actually understand quite a lot about this now. We have excellent tools to measure and quantify these processes. In terms of site characterization and assessment, in the early days there was huge uncertainty about capacity. That's been reconciled to a certain degree through the harmonization of methodology. It's still quite challenging if you go to a brand new, what we would call a greenfield site where there's not much known about it, a lot of work to characterize that in fact that the seal is good. Which is one of the reasons why oil and gas reservoirs or regions near oil and gas reservoirs are interesting, because the characterization work is very extensive there. In terms of storage engineering, I think we've identified sort of the single biggest risk is overpressuring by injecting too fast or not using enough wells. And this is a manageable problem by choosing more wells, or you may actually decide to try to relieve some of the pressure in the formation by extracting brine. So that's a possibility. The operations have been very good at all of these projects, and they've gone well in terms of safety. Lots of monitoring techniques, and I think I gave you a couple of examples. If we had all day, we could do a lot more. Another very important issue is contingency planning and remediation. It's fine to say, oh, we think the risks are low, but things happen. So one of the things we've done over the past couple of years is to really look at remediation methods. If you have a leak from a well, or sort of worse yet, if you had a leak up a fault or fracture, what would you do? And methods have been developed to deal with those issues. Regulations have been developed in many parts of the world. And then the final one is the financial responsibility. If you put CO2 underground, and it might be fine now, but say something happened in the future, you want to have some mechanism where there are funds available to remedy whatever needs to be done. And so in the short run, there are well-developed mechanisms for financial responsibility. Basically, you can buy insurance for these projects. Now, long-term liability depends from country to country, and some countries have sort of sorted it out and others haven't, so that's on the to-do list. So now, just very briefly, I just want to say one thing. What's different about CO2 storage for negative emissions than for capture from large-scale power plants and so forth? And I put this back up. E.J. Bike presented this earlier today. And this is an example of dividing those regions in the US where you had co-located storage and biomass for BECCS that sort of had a 50-mile radius. And if you did that and you looked at the amount of biomass you could collect and convert that to CO2, it turns out to be like 500,000 tons per year is sort of the mean size of the project. Okay, if we compare that to a typical geologic storage project like Sleipner or the one that you heard about from Microtomography, this is on the small side. And it would be even much smaller, as EJ said, if you didn't have this 50-mile collection radius. So that brings up some interesting issues about really economies of scale. That permitting, characterization, if you have to build pipelines, if you drill a well, a typical well might be able to store 1 million tons a year. Well, if you only have 500,000 tons, you still got this pretty big well. I mean, at some point, you really can't drill a smaller well. And monitoring, once you're, kind of in for a dime, in for a dollar if you're monitoring an area. So these BECCS projects, as an example, may be more expensive per ton of CO2 than people have been anticipating. So that's sort of the glass half empty view of it. On the other hand, I think there's another way, and I'm just about done, of looking at this, is that particularly if you had lots of small-scale projects like the 25 megawatt, biomass power plant, your CO2 could be, 50,000 tons a year. So maybe the idea of injecting supercritical CO2 as a separate plume isn't the best idea. Maybe there are clever schemes where you could dissolve all of the CO2 before it's even injected into the subsurface. And if you were to do that, you would basically accelerate opportunities for mineral trapping. You would completely eliminate the risks of CO2 escaping the storage formation and so forth. So there might be some clever synergies that could work out to the benefit of negative emissions because the projects are smaller. And I don't really know which way it's going to go now. So with that, I've taken 3 minutes too long. And anyway, thank you for your attention.